In this video, we're going to cover the 3 key techniques that you'll need to know when it comes to solving exponential equations. For those who don't know me, my name is Chris Iannazzoni. I used to work as an engineer for a defence company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. An exponential equation looks something like this. It differs from other functions because the power is the unknown rather than the base. There are 3 key techniques that we use for solving exponential equations, and these are equating exponents, using a quadratic solution, and using a logarithmic solution. Let's start by exploring the first method. The method of equating exponents is a 3-step process. It works best in the more simpler scenarios. In this example here, we have 3 to the power of x equals 27. Step 1 is to rewrite this equation so that both sides of the equation have the same base. In this case, we can convert 27 to 3 to the power of 3. Having done that, we can now ignore the bases and focus purely on the exponents instead, giving us the quick solution x equals 3. Now that was a fairly simple application, so let's try a bit of a harder example. Despite the difficulty, the method remains the same. We start by trying to get the bases of both sides to become identical. So to do that, we're going to convert our 25 into just 5 squared. From here, we can rely on our index laws to just expand that power of 2 through the rest of the exponent. Once we've done that, we can now equate the exponents and then just solve for x. Sometimes you'll get more complicated scenarios where equating exponents just isn't on the table. We perform a quadratic solution using the following framework, but before we dive too deep into that, let's take a step back and figure out when do we actually need to use a quadratic solution. The first key indicator that you're looking for are descending powers of x. In this example here, we have 2x down to just 1x and down to no x. Those are descending powers of x, and they are reminiscent of a quadratic, power 2, power 1, power 0. The next indicator is coefficients on your exponential terms, in this case the coefficient of 6 on our exponential. When you have coefficients, it tends to break the method of equating exponents. Let's check a quick example. If we had 3 to the power of x equals 3, then we have a very simple solution x equals 1. But as soon as that left-hand side is multiplied by 2, suddenly we're saying that 6 equals 3. Not good. Anyway, those will be the main things that I watch out for. Let's try and actually apply the quadratic solution to that example. The first thing that you would want to do in this situation is to rewrite all the exponential terms in your equation to share a common base. You've seen how this works in the previous example. In this case, there's nothing actually to be done here, so we can move on to the next step. The next step is to convert to a quadratic form, and we do this through substitution. We choose our substitution to be the largest common exponential term in the equation. We have 3 to the power of 2x and we have 3 to the power of x. The largest common term between those two would be 3 to the power of x, so that's what our substitution will be. If you want, you can even use your index laws to take that coefficient of 2 out the front as another exponent. That makes it a bit more obvious how you then use your substitution. Whatever method you use, you now have a quadratic after having subbed in a instead of 3 to the power of x. So we just solve it like we would for any other quadratic. This one I'm going to solve through factorization and null factor law. Now that we have our quadratic solutions to a, we can then sub in what a actually was, 3 to the power of x, into those equations. And from there, we just solve each of those equations individually. In this case, we only have one equation that actually gives a valid solution. 3 to the power of x equals -9 will never have a real solution. If x gets larger, then the number is going to get larger, and if x gets smaller, then it's actually just going to trend towards 0, never go negative. The last method of solving exponentials is with logarithms. It should go without saying, if you haven't been introduced to logarithms yet, check that out first. Otherwise, let's continue. Typically, we use a logarithmic approach when neither of the other 2 approaches have worked. Let's give it a shot. The first thing we want to do is get the exponential term on its own. In this case, all it takes is a division of 5. Now that we have the exponential on its own, we're just going to swap to logarithm form, and that's it. We've got x on its own. That's all it takes. Since x was in the exponent, and switching to logarithmic form brings the exponent down to the front, then we've achieved what we needed to do. We got x on its own. As a bonus, let's see how to handle exponential inequalities. Now, we're also going to use a logarithmic approach for this type of equation, but it's going to be a little bit different to just straight up converting. We use the following framework for this type of question. Let's check an example. Step 1 is to get the exponential on its own. In this case, there's nothing to be done here, so we move on to step 2, which is applying the logarithm. Now, when it comes to applying the logarithm, you can technically choose any base you want. My recommendation is that you choose the base of your logarithm to be identical to the base of your exponential. That way, when you do your simplification, you're only going to have one logarithm at the end instead of two. Just be mindful. When you use a logarithm that has a base between 0 and 1, the direction of your inequality needs to flip. Having done that, we just need to get x on its own. And we do that by using the power law of the logarithm, bringing the power out the front. Then we can also cancel that logarithm out, since any time the base and bracket are identical, that logarithm is equal to 1. Okay, now let's see what happens if we chose a different base instead. Let's try the natural logarithm, which is just log e, where e is approximately 2.7. The reason I mention that is because, as I mentioned earlier, if you have a base between 0 and 1, you need to flip the direction of the inequality. Because e is approximately 2.7, we don't need to do that. But okay, fair enough. All we're going to do now is follow the same steps as before. We use the power law to take the exponent of x out the front, but here's the difference. We can no longer cancel out that logarithm, so we have to divide both sides by the logarithm. Here's the issue. Is that logarithm positive or negative? Because if it's negative, we need to make sure that we flip our inequality. But when it comes to logarithms, I don't know about you, but I find it hard to figure out immediately, at a glance, is this negative or positive? You can figure this out pretty quickly by converting to an equivalent exponential form. If the natural log of 0.4 is equal to some value, let's call it y, then we can write an equivalent expression by saying e to the power of y is equal to 0.4. Now here's the tricky bit. We need to figure out what exponent of e is going to make it equal to 0.4. Well, let's try the possibilities. If our exponent is larger than 1, then, well, we're going to get greater than 2.7, so we could ignore everything greater than 1. The next thing we could look at is if our exponent is between 0 and 1. Exponents between 0 and 1 behave like roots, which just means you're looking for a number that when multiplied by itself a bunch of times gives you 2.7. And we know that 0.4 will never get there because when you multiply decimals between 0 and 1, the numbers actually shrink. That leaves the only possibility to be negative. So we know that our logarithm is negative. So going back to our actual question, when we divide by that logarithm, we now need to flip the inequality signs. So one of those was significantly more effort than the other. I'll let you choose which one you want to use. The only reason I mention the difference is because when the CAS solves these inequalities analytically, it tends to defer to using the natural log instead. So when you get your answer on the CAS, it's going to have two natural logarithms as part of its answer. I just wanted to show you where that came from. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.